In this lesson, we will discuss some important thermal properties of matter. When heat is supplied to an object, what are the changes that you can expect in the object? Well, you know that heat is a form of energy. That means when you give energy to matter, the atoms and molecules will behave differently. Is that right? Because heat is a form of energy. Now, what kind of different behavior will atoms and molecules have? Their kinetic and potential energies can change. That means molecules and atoms will vibrate or move about with larger amplitude. When molecules want to oscillate with larger amplitude, they need a larger space to occupy. So one of the most prominent effects of supplying heat to an object is thermal expansion. An object expands when heated. All right, we will start looking at expansion, thermal expansion first. Heat supplied to a material will increase the internal energy and causes the molecules to vibrate with larger amplitude. As a result, each molecule now takes up a little more space than it had occupied earlier, which results in the expansion of the material. Now, as a result of expansion, its length, area, and volume will increase. Now, if an object is like this, most dominant change will be an increase in length. On the other hand, if the object is a flat surface, the most dominant change would be the change in area and obviously a change in volume. Well, if an object increases its volume without changing its mass, that means its density will change. So heating an object can change its density. What do you think? What kind of density change can occur? Is it an increase in density or a decrease in density? Well, think about it. Now, we will consider each of these changes separately. Let's start looking at the change in length when heat is supplied to an object in the form of a rod. Okay. Now, here I have a rod of original length L0 at a temperature T0, and its length increases by a small quantity delta L when the temperature is increased to T sub F. Now, in future, in place of T0, we will use T1, and for TF, we will use T2. Temperature increases from T1 to T2 or T0 to TF. So the length of the rod at the temperature T0 is L0 and its length at a temperature TF is L0 plus delta L. When an object is heated, its length increases. The increase in length delta L, what are the factors on which the increase in length of an object depend on? If I start with a longer rod, the increase in length will be greater. Is that right? And also, if I heat it through a greater temperature, the increase in length will be greater. So these are the two dominant factors on which the increase in length depend on. So the increase in length delta L is directly proportional to the original length and the change in temperature. Can you write that as an equation? We can write it as delta L is directly proportional to L0 delta T. And you know by now, a direct proportion can be replaced by an equal sign adding a constant. So delta L equal to alpha L0 delta T, where alpha is a constant for a given material. It is called the coefficient of linear expansion, or sometimes it's called the linear expansivity. Alpha is a constant called the coefficient of linear expansion. And what is the value of that? If you write an equation for it, alpha equal to delta L divided by L0 delta T. So what is alpha? Can you give me a sentence describing alpha? Alpha is a measure of the increase in length per unit length per Kelvin rise in temperature. In other words, if I take a rod of length 1 meter and heat it by 1 Kelvin, the increase in length at that time will be a measure of alpha, the coefficient of linear expansion. It is a measure of the increase in length per unit length per Kelvin rise in temperature. Tell me, what is the unit for measuring alpha? Can you look at this equation and tell me what is the unit for measuring alpha? If you look at the right hand side, delta L is measured in meter. The original length L0 is measured in meter, so the meter and meter will cancel. The only unit that survives is Kelvin on the denominator. So alpha is measured in a unit called per Kelvin. There you are. So the unit of alpha is per Kelvin. Let's now talk about an experiment to measure alpha. That will be an experiment that you will be doing in the lab. Now here is the experimental setup we will use to measure the value of alpha for a rod like this. In fact, this is part of that experiment. I have taken from one of those experimental kits to use it as a rod to point on the board. Well, if you look at this, this is called a steam jacket. Now, I have that equipment right here. This is the steam jacket. I can take it out. Now, the rod whose alpha is got to be measured, you start by measuring its initial length L0 and then insert it inside the steam jacket. There you are. And keep it back in there. And what is the specialty of this? Now, the rod is now in contact with this screw, which is fixed. That means the rod cannot expand that way. And on this end, you have a micrometer screw, which can be turned so that a space can be left in here. You can see where I'm pointing. There is space and the rod can expand there. Now, once you have a space there, you can pass steam through here. The steam will go into the jacket and then out through the other end. And after passing steam through this for about 5 or 10 minutes, the rod will expand. And now work the micrometer screw back. You can measure the increase in length. So once you know the increase in length, the original length, and the rise in temperature, we can calculate the value of alpha. Is that right? The coefficient of linear expansion. So in the steam jacket, you can use the thermometer to measure the initial and final temperature. You can measure the initial length before you put the rod in there, and the micrometer can be used to measure the increase in length. Okay, so the length of the metal rod L1, as I had told you, in place of L0, I'm going to use L1. The original length at T1 degrees Celsius is L1, and that is measured at the room temperature. And the arrangement shown here, we will use that to measure the length L2 at a temperature T2 after passing steam through the jacket. And once you have those measurements, we have delta L equal to L2 minus L1 and delta T equal to T2 minus T1, and that will be enough for us to make our calculation. Alpha equal to delta L divided by L1 delta T, and that will be delta L is L2 minus L1 and delta T is T2 minus T1, and this will give you a measure of the coefficient of linear expansion. Let's now solve this equation for L2 minus L1. Can you do that? Alpha equal to L2 minus L1 divided by L1 times T2 minus T1. Therefore, L2 minus L1 equal to alpha multiplied by L1 times T2 minus T1. And in this equation, we can solve for L2 if you move L1 to the right side. You have L2 equal to L1 plus alpha L1 T2 minus T1. I can factor out an L1 on the right hand side. Let's do that. That will be L1 times 1 plus alpha delta T. L2 equal to L1 times 1 plus alpha delta T. A very important equation which will help you to find the length of this rod at a higher temperature if you know the original length at T1 degrees Celsius, the change in temperature, and the coefficient of linear expansion. We will use that to solve problems. Well, let's now talk about the change in area. Now, if you have an object like this, for example, a flat object, when it is heated, its length will increase, its width will increase. As a result, its area will increase. Change in area, and we can actually define similar quantities that we defined for linear expansion in this case as well. Similar expressions can be written for the change in area with temperature, and what are those? The change in area delta A is directly proportional to the original area and the change in temperature. And when you write it as an equation, it becomes delta A equal to beta A delta T, where beta is a constant. And what will you call that constant? Well, you can call it the coefficient of area expansion or area expansivity. Beta is called the coefficient of area expansion. Can you give me a definition for it? What is coefficient of area expansion? If you solve for beta, what will that equation look like? Beta equal to delta A divided by A delta T. It is the increase in area per unit area per Kelvin rise in temperature. Can you tell me what the unit of beta will be? Well, the same unit as we use for alpha. Why? delta A is measured in square meter, A is measured in square meter, those will cancel. The only unit that will survive is Kelvin on the denominator. So beta also is measured in per Kelvin. And delta A is A2 minus A1. Delta T is T2 minus T1. So we can write beta equal to A2 minus A1 divided by A1 times T2 minus T1. Can you use this to solve for A2 the way we did solve for L2? Well, it will be A2 equal to A1 times 1 plus beta T2 minus T1. The same kind of equation we had L2 equal to L1 times 1 plus alpha T2 minus T1. Similarly, A2 equal to A1 times 1 plus beta T2 minus T1. Since area is made up of two lengths, what does that mean? Area is made up of two lengths. Now, if you look at this area, this is made up of a length and a width. Width also is a length, is that right? That means there is an increase in length this way and an increase in length this way. That means an increase in area involves increase in length twice. Therefore, what do you think you can write an approximate relation between alpha and beta? Alpha is the coefficient of linear expansion. Beta is the coefficient of area expansion. Therefore, we can say beta equal to 2 times alpha. Why? Because beta involves the increase in length twice. An increase in area is made possible by an increase in length twice. Therefore, beta, the coefficient of area expansion, is 2 times the coefficient of linear expansion. And similarly, we can write expression for the change in volume. All right, what are those expressions? We can say the increase in volume is directly proportional to the original volume and the change in temperature. And you can write the equation as delta V equal to gamma V delta T, where gamma is a constant, and what will you call that constant? You can call it the coefficient of volume expansion or coefficient of cubical expansion or cubical expansivity. Any of those is applicable for that. So gamma is a constant. We call it the coefficient of volume expansion. And what is the definition you can give for coefficient of volume expansion? If you can solve for gamma, all right, what is gamma equal to? Gamma equal to delta V divided by V delta T. Gamma is a measure of the increase in volume per unit volume per Kelvin rise in temperature. And therefore, what is the unit for measuring gamma? It is measured the same unit per Kelvin. So the unit for alpha, beta and gamma are all the same, namely per Kelvin. Alright, rewrite this. Delta V is V2 minus V1 and delta T is T2 minus T1. And therefore, if you solve for V2, what will that be? V2 will be equal to V1 times 1 plus gamma times T2 minus T1. And that way we will be able to measure the volume of an object at a higher temperature. Alright, can you tell me what will be a relationship that you can write between alpha and gamma? When you want to measure the volume of an object, you see, volume of an object involves length, width and height, and each of this is a length. Therefore, when you talk about increase in volume, it involves increase in length 3 times. Therefore, what is an approximate relation between alpha and gamma? We can say gamma equal to 3 alpha. Gamma involves 3 times alpha. A change in volume involves increase in length 3 times. Now, let's put those approximate relations alpha, beta, gamma one more time. Assume that each of the following objects is heated by 1 Kelvin. That is delta T equal to 1. Alright, that means if the definition of alpha is increase in length per unit length per Kelvin rise of temperature, when you heat an object by delta T equal to 1, the increase in length will be a measure of alpha. The increase in area will be a measure of beta, and the increase in volume will be a measure of gamma. So if each of these is heated by 1 Kelvin, the increase in length per unit length will be alpha. Now, this is supposed to be alpha there. So let's say this is alpha. This is 2 alpha. So, when each of these is heated by 1 Kelvin, the increase in length per unit length will then be alpha. The increase in area per unit area will be beta. Beta is 2 times alpha. And the increase in volume per unit volume will be gamma. And that gamma will be 3 times alpha. Okay, let's move on. Let's now look at some values of alpha and gamma for some common materials. It will be very useful for solving problems. The alpha value for aluminum is 24 times 10 to the negative 6 per Kelvin. In other words, what it means is if you take 1 meter aluminum like what I am holding and heat it through 1 Kelvin, its increase in length will be this much, 24 times 10 to the negative 6 meter, which is 24 micrometer. It's very small, is that right? And brass, if you take 1 meter of brass and heat it through 1 Kelvin, its increase in length will be 19 micrometer. Lead, 29 times 10 to the negative 6. And of course, you have the value of gamma. And you can see the value of gamma is approximately 3 times, not exactly, approximately 3 times the value of alpha. So in a problem, if you need gamma, but I give you only alpha, what will you do? Assume that gamma is 3 times alpha. Okay. In the beginning of this lesson, I told you, when there is a change in volume without changing the mass, that will result in a change in density. So, change in density with temperature. If I heat this metal rod, this aluminum rod, its mass will not change, but its volume will increase. As a result of the increase in volume, the mass per unit volume will now be less, and that means the density will decrease. So, if you heat a volume of air, the density of that air will decrease. And if the density of air decreases, that air will rise. You see, that's a very important phenomenon in nature. Hot air will rise and cold air will sink. You can create an air current by heating one part of air. You can do the same thing in water. If you heat one part of water, the hot water will become less denser and rise. Cold water will sink, and we will see this phenomenon in the next part of this lesson. Alright, when an object is heated, its mass remains the same while the volume increases, and as a result there will be a decrease in density as the temperature increases. Consider an object of mass m. If V0 is the volume and D0 the density of the object at 0 degrees Celsius, we can write D0 equal to mass divided by volume. Is that right? D0 equal to m divided by V0. The density at 0 degrees Celsius is its mass divided by its volume at 0 degrees Celsius. Well, that gives us m equal to V0 D0, or m equal to D0 V0. Now, if Vt is the volume and dt the density at T degrees Celsius, then what will an equation for dt will look like? dt will be mass divided by Vt. Will the mass change? No, it will not. The mass is the same. But the volume changes from V0 to Vt. Therefore, I can now write, well, do you remember we said V2 equal to V1 times 1 plus gamma T2 minus T1. T2 minus T1 is delta T. And our V1, in place of V1, we have V0. So we can replace this V sub T as V0 times 1 plus gamma delta T. And what happens here? V0 and V0 will cancel. So density of that object at a higher temperature T degrees Celsius, dt equal to D0 over 1 plus gamma delta T. We can write this in a simpler form by using the binomial theorem. Well, I don't think many of you know binomial theorem. I'm going to give you simply that approximation. Using binomial theorem, this can be approximated as dt equal to D0 times 1 minus gamma delta T. So density at a higher temperature equal to density at 0 degrees Celsius times 1 minus gamma delta T, where gamma is the coefficient of volume expansion and delta T is the change in temperature. Well, there is a small exception for this rule, the change in density. Now, what is that exception? Now, here according to this equation, every object decreases its density as the temperature increases. What does that mean? It means the density decreases the density increases as you cool down the object. Is that right? Well, there is an exception. Let me spend a couple of minutes to talk about that. That exception is water. Well, if you cool water, its density will increase, just like any other substance. If you cool down this aluminum, its volume will decrease, and that means its density will increase. Now, when water is cooled down, its volume decreases, that means its density increases, so cold water will sink and warm water will rise. But for water, this particular property now is true only until the temperature reaches 4 degrees Celsius. That means as you cool down water from the room temperature to 4 degrees Celsius, its density will keep on increasing. But if you cool down water from 4 degrees, as the temperature lowers further, the water instead of contracting, it begins to expand. Now that is the behavior that you see only for water. This is called an anomalous behavior, something that is different from the normal. When water is cooled down from 4 degrees down to 0, instead of its volume decreasing, its volume begins to increase. And that is the reason why when you put a bottle of water in the freezer, when it becomes ice, the bottle breaks. Why? Because when water cools down from 4 degrees Celsius to 0, instead of its volume decreasing, its volume increases. Now, this is a particular characteristic of the crystal structure of water. The hydrogen bonds that hold the water molecules together has this peculiar property, thereby their spacing increases as the temperature approaches the freezing point. Now, we will not go into the details of it, but there are some very important implications of this phenomenon. Wow. Why is that? You suppose on a very cold day in a very cold region, a lake or a river can freeze. Now, when it freezes, where does ice begin to form first? Will ice begin to form at the bottom of the river or at the surface? Well, ice begins to form at the surface. Why? Because as the temperature of water decreases below 4 degrees Celsius, its density, what happens to density? Density decreases. Now, how does the density of water change? If I draw a graph of temperature against density, now this is 4 degrees Celsius. If you cool down water from room temperature to 4 degrees, its density will increase. There you are. Suppose this is 20 degrees Celsius. You cool down, the density will increase, and the density of water is maximum at 4 degrees. If you cool down water now, its density decreases. So, the density, water has a maximum density at 4 degrees. When water begins to cool below 4 degrees, its density decreases and will rise. That means it rises to the top and there it freezes. So ice begins to form at the top of the water first. Now this has great implications for life in water. You see, when it is very, very cold, if ice begins to form at the bottom, that will actually kill all the life in water. Fish or any animals that live in water will find it very difficult to live. Because ice begins to form at the surface, that will form as a barrier between the very cold air outside and the water below it. That will keep the water below warmer, thereby keeping a good environment for animals to flourish. You see, look at nature's dance. Nature plays such enormous tricks to keep its own safe and sound. All the aquatic animals are able to survive in very cold climates because of this property of water. That is, it has an anomalous behavior. When it is cooled down below 4 degrees Celsius, its volume begins to increase. Density begins to decrease. All right, let's now use the concepts we developed so far to solve some problems. All right? Okay. A steel rule has a length of 30 centimeter at 20 degrees Celsius. What is its length at 100 degrees Celsius? Alpha for steel is 11 times 10 to the negative 6 per Kelvin. Well, what all we need to do is the equation we developed, L2 equal to L1 times 1 plus alpha delta T. Delta T is T2 minus T1. We got our initial length 0.3 meter. We've got a change in temperature 100 degrees Celsius minus 20 degrees Celsius, that is 80 Kelvin. Remember, a difference in temperature measured in Celsius and Kelvin are exactly the same. So 100 degrees Celsius minus 20 degrees Celsius is 80 Kelvin. Alpha is 11 times 10 to the negative 6 per Kelvin. L2 equal to L1 times 1 plus alpha delta T. We have all these values. So replace these quantities by their values and use your calculator to evaluate this. Okay, that should give you 0.30026 meter is the length of that steel rule at that higher temperature. That means if you use a steel rule for measuring length, as the temperature increases, the length measured will not be accurate because the length of the ruler changes. All right, let's look at another problem. A bridge 100 meter long is built of steel. By how much will its length change from the coldest winter of negative 30 degrees Celsius to the hottest summer of 40 degrees Celsius? Well, what we need to find here is delta L. We know delta T, we know the original length. Can we find delta L? What's an equation that we can use for delta L? Well, delta L equal to L1 alpha delta T. Is that right? All right, we got L1 100 meter. Delta T is final temperature minus the initial temperature. 40 minus negative 30, that is 70 Kelvin. Alpha is known, therefore delta L is alpha L delta T. And using all the given values, that delta L is 0.077 meter. Look at this. When temperature increases, the length of the bridge increases. So, if you are training to be an engineer, a civil engineer for example, Tell me, is it safe to build a bridge between two fixed columns? If you build a bridge, suppose this is a bridge built between two fixed columns. Is it safe to build it like this? When the temperature increases, the length is going to increase, and if it is built between two fixed columns, there is nowhere for the bridge to increase its length, so what's going to happen? It's going to buckle and break. So in order that the bridge may remain safe, bridges are normally erected on rollers so that there is room for expansion and movement. The same thing can be found in the construction of railway tracks. The rail tracks, there are spaces left in between rail tracks to allow for expansion. If expansion is not taken care of, rails expanding against each other will buckle and then derail the train, can cause great accidents. If you look at your driveway, when concrete slabs are placed to build your driveway, now do we make one full concrete slab for the whole driveway? No, we don't. We break them into slabs and allow a space between them. Why? Because when temperature increases and decreases, cold winter to warm summers, there are tremendous changes in temperature, especially in Florida. That means the concrete slabs will be expanding and contracting. We got to allow space for this to happen. And if you don't allow space for this to happen, the concrete will crack. Now, if you look at some driveways, you can see those cracks where those spaces were not properly provided. So all these have great application in building industry, in civil engineering. Okay, let's do another example. The density of aluminum is 2.7 times 10 to the 3 kilogram per meter cube at 0 degrees Celsius. What is the density of aluminum at 200 degrees Celsius? Again, what all you need to solve this problem is the relation between density at T degrees Celsius and density at 0 degrees Celsius. What is that equation? dt equal to d0 times 1 minus gamma delta T. So we need density at 0 degrees Celsius, that is given to us. We need delta T, that is given to us, is that right? From 0 to 200 degrees Celsius. We need gamma, the coefficient of volume expansion, but we are given alpha. If you know alpha, do we know gamma? Yes, because gamma equal to 3 alpha. Alright, D0 we know, delta T we know, and gamma is 3 times alpha, and that also we know. We go to our equation straight away. D sub T equal to D0 times 1 minus gamma delta T. Now replace all these values, and there you have 2.66 times 10 to the 3 kilogram per meter cube is the density at that temperature. You can see the density has decreased considerably when the temperature is increased. Alright, another one. A hole is drilled in an aluminum plate with a steel drill bit which has a diameter of 6.24 centimeter at 20 degrees Celsius. In the process of drilling, the temperature of the drill bit and the aluminum rises to 168 degrees Celsius. What is the diameter of the hole in the aluminum plate when it has cooled down to room temperature? Well, in order to do this problem, we need to break it down into two pieces. The first one is the drill bit. Suppose this is the drill bit. As you keep drilling it, its temperature increases. The temperature of the drill bit increases from 20 degrees to 168 degrees. So the diameter of the drill bit increases. Now remember, diameter is a length. So you can use the equation L2 equal to L1 times 1 plus alpha delta T to find the diameter of the drill bit at that high temperature. Now, once you know the diameter of the drill bit at the high temperature, the instant when you finish drilling the hole, the diameter of the hole is also the same value. And now what is the second part? The hole will now cool down, and you need to find the diameter of the hole when it cools down to the room temperature of 20 degrees Celsius. Alright, let's start the problem. You know, now don't confuse here, this D is not density. D20, what I mean is diameter of the drill bit at 20 degrees Celsius. That is what this D20 means. Diameter of the drill bit at 20 degrees Celsius is 0.0624 meter, 6.24 centimeter. The change in temperature of the drill bit is 168 minus 20, that is 148 degrees Celsius. Alpha for steel, can you remember that value? Well, alpha for steel is 11 times 10 to the negative 6 per Kelvin. The diameter of the hole at 168 degrees Celsius is the diameter of the drill bit at that temperature. So we can use the equation LT equal to L20, where L168 equal to L20 times 1 plus alpha delta T. And in place of L, we can use D, diameter. So D2 equal to D1 times 1 plus alpha delta T, where alpha is for steel. Well, we have all these values. Let's use those values there. D1 is 0.062 and alpha 11 times 10 to the negative 6, and the change in temperature is 148. That is 0.0625 meter. That is the diameter of the drill bit at the high temperature, which is the same as the diameter of the hole in the aluminum at that temperature. Alright, so diameter of the aluminum hole at 168 degrees is 0.0625 meter. Now it's going to cool down to room temperature. If dA1 is the diameter of the hole at 20 degrees Celsius and dA2 is the diameter of the hole at 168 degrees, A are used for aluminum. Diameter of the hole in aluminum at temperature T1, dA1, the diameter of the hole at 20 degrees Celsius. That is what we want to calculate. dA2 is the diameter of the hole in the aluminum sheet at T2 equal to 168 degrees Celsius. Then we have dA2 equal to dA1 times 1 plus alpha aluminum times delta T. Is that right? Yes. This is like L2 equal to L1 times 1 plus alpha delta T. Remember, in the previous equation, we were using steel because we were finding the diameter of the steel bit. So alpha value was for steel. This time, it is the hole in the aluminum, and therefore it is the expansion of the aluminum that we got to use, alpha for aluminum. We need to find dA1, so let's put down all the values. dA2 we know is 0.0625 meter. dA1 we need to find, and all these values, the alpha for aluminum is 24 times 10 to the negative 6 per Kelvin, and the change in temperature is 148 Kelvin. So simplifying the right hand side, we get 0.0625 equal to 1.00355 dA1, and therefore we can find dA1 as 0.0625 divided by 1.00355, and that is 0.0623 meter. That will be the diameter of the aluminum hole at that lower temperature. Now look at this. The diameter of the aluminum hole at a higher temperature, at 168 degrees Celsius, is 0.0625, and when the aluminum sheet cooled down to 20 degrees Celsius, the hole has shrunk. Its diameter is now 0.0623 meter. Alright, I want therefore you to think about this and give me a feedback. Just send me a line. An aluminum sheet with a hole at the center is heated to a higher temperature. Will the hole become bigger or smaller? Why? You have an aluminum sheet with a hole drilled at the center. As you increase the temperature of the aluminum sheet, will the hole become bigger or smaller? Why? Would you like to send me a line or two about it? Well, I might even give you a point if you do that well. It's a very important concept, all right? I want you to give it a thought. Okay, I'm going to stop this lesson here, and I will continue with this lesson, which is transfer of heat energy, in the next part. Okay, I will see you for that shortly.